So the camera literally just randomly fell off of the books, and so we're starting back up again. So if you all saw like the floor getting closer to you, it wasn't an earthquake, it just fell. Okay, so anyway, so back to our story. So just don't say, hey, as time increases, position increases. You need to say time increases as like a quadratic function, or it's an exponential function of time, something like that. And then I also want, like on that equation, you can just do something simple. You can just do y equals kx squared, okay? If you're a nerd and really like to punch numbers into your calculator, you can plug in numbers and you'll see that that k value has a numeric value of 4.9. If you did that, great, don't worry about it, you don't have to. All I'm looking for is that you realize that it's a quadratic function, okay? That's all. Now, on number 15, said, this isn't linear, okay? But what I'm saying is a huge if, okay? If had been a linear function, okay, and it's not, but let's just say it had, okay? Then I'm asking you, what physical quantity would be represented by the slope? So, I've got this position in meters, right? So if I were to calculate the slope, I'd have change in y over change in x would be change in meters over seconds. So what physical quantity is measured in meters per second? Velocity. Okay? What's Rose?
That's not what I had.
What did you
I
have?
just said it would have been a direct variation between the x and y axis.
What physical quantity?
Okay, I didn't understand the question, okay?
When I ask for a physical quantity, it's like mass, acceleration, velocity, squirrels. Okay? Maybe the slope represents squirrels. I don't know. Okay? And then I would say, and how would you know? Here's all you have to say. I know it's velocity because change in y over change in x gets me units of meters per second.
Okay.
Okay? That's it. Don't make it difficult. Now, here's what I want you to see. Okay? And this is this whole key on number 16. Using your answer number 15, explain the shape of the graph. So, here I've got a steel ball. Okay? And I'm going to let this thing fall. So, as soon as I let go of it, one of two things can happen. Okay? It's either going to maintain a constant velocity or it's going to accelerate. Okay? Literally. Every motion that we're going to study in this class can only be one of two things. It's either constant velocity, meaning that the velocity vectors aren't changing, either getting bigger, getting smaller, changing direction, or it's accelerating and something is changing. It's speeding up, it's slowing down, it's changing directions. One of those three things, right? So the other thing you'll hear me talk a lot about and is called Jedi Stoffel law. We'll get into Jedi Stoffel law later. The Jedi Stoffel law means you stop the force and you watch, okay? So if I've got this marble and I stop applying a force to it by holding it with my hand, and I watch what happens, okay? So as soon as I let go of it, right, I stop applying the force from my hands and I watch what happens. Oh, it begins to accelerate. The only way that's going to accelerate, what? Hold on. Thanks, folks. More technology. There you go. So the only way something can accelerate, speed up, slow down, or change the direction is if an outside force acts on it, because Mother Nature is a lazy prima donna. Okay? That's it. Mother Nature is a lazy prima donna. So the only way something can speed up, slow down, or change direction is if you apply a force. So when I let go of it, okay, and I see it begin to accelerate, I know there has to be some force acting on it. Otherwise, it would just stay there, which would be really cool. So if I let go of this and it just stays there, you all would be like, oh, you're a witch, okay? No, it's just because there's no outside force acting on it. So when you look at something falling and it's accelerating, as it falls, it goes faster and faster and faster. So this is a logic problem, okay? So when I drop this thing, on the slope of this position time graph represents velocity, okay? And this is why I'm just throwing this in, because the next unit is all going to be about this graph. So the slope of the line represents velocity. So you know when something falls, it goes faster and faster and faster. Well, how we represent that is the slope of this line getting continuously steeper and steeper and steeper. So because the slope represents velocity and things fall faster, therefore the slope gets steeper and steeper and steeper. So on that last question, on 16, explain the shape of the graph. All you have to say is that as it falls, the object speeds up, so therefore the line becomes steeper because the slope represents velocity. So the only way this could be a straight sloping line is if I let go of it and it fell at a constant speed like this, okay? If it falls at a constant speed like this, then it would be a straight sloping line. But because of the fact that it falls faster and faster and faster, the line becomes steeper and steeper and steeper.
Does something like a leaf have like a linear line? Or?
Oh, it does. So when we do gravity, and physicists are famous for this, we just leave out things that like complicate things like air friction. We just leave that out. Okay? Yeah, obviously if you drop like a tissue paper or a leaf, it's going to reach a constant velocity, and this would become a straight sloping line. Okay? But what we always assume, because that gets complicated, then you have to calculate drag coefficients and all sorts of weird stuff. Okay, now make sure on number 7, okay, where I've got determine the slope of the line, showing the values that are chosen, and it has the correct units. Okay, so on number 7, depending upon which points you pick, your slope should be something around 0.6, and it should be have units of, you can either put it as 1 over kilograms, or you can put kg to the minus 1. Okay, so make sure on number 7 that you have your slope is something around there, and you have the correct units. Now, when you get to number 8, because this is a linear function, I tell you, here's how I want this played out. I tell you, like, for example, if the acceleration is graphed on the y-axis, then put an A for the y. So number 8, you should have acceleration, because that is what's graphed on the y-axis. Don't put in the units here, okay? I just want the acceleration, because acceleration is shown by the letter A. And then you're going to have your slope, okay, something around 0.6, and then 1 over kilograms. And then you're going to have force. So everybody's answer on number 8 should look something like this. The only variation is going to be what you're going to have here for your numeric value of your slope. But it should be something around this. Now, this is where the magic happens. Is when you get down to number 9, okay, using the equation, determine the value of the force required. Now, here's the deal. Let me give you a hint in case you haven't figured this out. I'm all about the process. So on number 9 and number 10, if I don't see how you got that answer, it's a train wreck. I'm not giving you full credit for it. It's like, okay, great. I don't know how you got the answer. You randomly put down an answer. Okay? So what I'm looking for on number 9, you're trying to find that force, right? So you can have acceleration divided by your slope is going to equal your force. So you want an acceleration of 15 meters per second squared. Now, again, this is why you have to pay attention to units. You're going to divide by your slope, and that has units of 1 over kilograms. So what happens is this denominator is in the denominator of the denominator. This is where this kilogram is. So it flips up, you get kilograms meters per second squared. That's what force is measured in. Okay? Now, if you just have a number here without any units, and nothing's here, you still get units of meters per second squared. Okay? Because you don't have anything down here to introduce units of kilograms. So that's why it's so important that you work that through in terms of a grand idea and you pay attention to those units. Okay? Are we good? Anything else you want me to go over? Anything at all? Okay. So, I want this assignment hopefully by like 6 o'clock this afternoon. Right? And you of my classes, you guys have done the best so far as getting stuff in. So that's cool. All right. Nothing else? So when you do this, again, here's what I want. Like works, one, and then like just like graphing assignment. Okay? Something like that. So that I know it's hers, I know it's coming out of first block, and then I know what that is. Okay? That's how I sort things out. Okay? Once, twice sold. All right. So, check one thing. I hate Zoom. Hold on. See, this is what annoys me. Lord, see technology. So see if Ellie shows up on.
Okay.
Okay. This makes sense in just a second.
So tomorrow, is there gonna be like a Zoom call or what?
Yeah, I've got it, theoretically, I should have sent out an email.
Yeah, you have a Wednesday Zoom, right?
Yeah,
Oh, okay.
what I can't figure out is that it shows up, like, that's the link that I sent out to everyone. So then like Ellie's trying to join it. Somebody have the Chromebook.
Yeah.
See if you can join, let's do this, see if you can try and join this Zoom meeting. Because I gotta figure out why it's not working. And that's the frustrating thing right now is that it's like, oh, anyway. I need coffee. That'll make everything better. Okay. So, is the camera still going? Okay. All right. So here's the deal. If you look at where we're at in terms of this journey to physics enlightenment. So we figured out what units we're using. We figured out how to do graphs. We figured out how to do dimensional analysis. So here's the last big thing that we need to figure out, and that's how do we write down our numeric answers. So if you think about every answer you're going to write in this class, you have two decisions to make. You have to decide how many digits you're going to write and what units that you're going to put down. Okay, literally, every answer that you write in this class, those are the two decisions that you have to make. So, as we go through this, and these rules of significant digits and things like that, did you ask to join?
Yeah, it just says please wait for the host to start this meeting.
Okay, so here's what's weird is that that's the meeting that I have going right now.
Yeah, cause like yesterday, I just went the Wednesday one, like the link for the Wednesday, and that's what worked.
Yeah,
Is that
I
not
used
the
the
one that we're
Wednesday
supposed-
link too.
Is that not the one we're supposed to use?
What do you mean? It should be the one for like first block, there should be a recurring one for first block.
On Google Classroom, there wasn't anything. So
Well, I hate Google Classroom.
well, I looked on my email, and the Wednesday one was the only one that was there, so I just clicked on that, and that's what was working, so.
Hold on. Ah! And it doesn't show up that he's waiting to join, does it, Maddie?
Mm-mm.
On that? Hold on. I'm gonna try something else. Okay, Josh, I just theoretically sent you that link.
Mm-hmm. The email?
Yeah, in an email. Did you get it?
Let me close out this first. So,
Any luck?
oh, yeah. Did it work?
Mm-hmm.
Okay.
So I'm just have to send out, I
Oh,
guess, that
there's
email
Ellie.
every morning.
Ellie's on.
Yeah.
Okay. Well, that mystery is solved. So much for technology and mass links being sent out.
I bet you could send it out once and then we could just re-click on it every time.
Could we use the Google Classroom, like if you just put a link on there so we can just go there and click that? Like, just for that?
I'll try that.
Okay. It's like that's what a lot of other classes
Google
have.
Classroom and I don't play nicely together. Okay. All right, Ellie, hopefully now it works and life is good, and sorry about that. Anyway. Okay, so here's the deal. When you talk about measurements, what limits our ability to verify that our equations are working is our ability to measure things. So for example, if you look at what physicists try and measure, you try and measure extremes. Like, hey, what's the mass of Jupiter? Okay, well, it isn't like we can grab Jupiter and put it on a scale and go, oh, here's the mass of Jupiter, okay? Or how far away is, the nearest star? Okay, Proxima Centauri. So, how do you measure that distance? How do you measure, on the other extreme, how do you measure the mass of a single neutron? It's like, or a proton or an electron. Like, how do you get those numbers? So, there's two different terminologies, and these are on the lecture notes that you've got. You have precision and you have accuracy, okay? So you have to keep these two things straight. So accuracy is referring to an accepted value. So imagine that you're trying to hit a target, okay? So accuracy would be how close you come to hitting the bullseye. So if you're talking about accuracy of a measurement, you have to have an accepted value. So this is like the Google thing. If you can Google an accepted value and find it, you can talk about the accuracy of the measurement. So if I said, hey, what's the accepted value for the gravitational acceleration on Earth? You could pull that up and it would say, oh, 9.80 meters per second squared. Okay, hey. So then when we do a lab and we try and find an experimental value for that, then we can compare that to 9.80 meters per second squared. we're gonna try and find the distance to the moon. Hopefully NASA knows like how far away the moon is. We can compare our data to that distance. So, to talk about accuracy, you have to have an accepted value, okay? Where things go south, and the difference is if you talk about precision. So precision is basically how good is the measurement in terms of your data, okay? So I've given you all an index card, okay? So for those of you that are watching at home, the kids have an index card. And they also have an arbitrary measurement device that I've called a widget, okay? So some of these widgets just have a 0 and a 1, okay? Some of them have like this, right? Here's 0 and here's 1. So here you have these that are marked off in tenths, okay? And then you have some that are like this, okay? So there's 0.1, there's 0.2, okay? So the difference is, between these three, is the number of divisions. So one is just 0 and 1. This one is marked off in tenths. This is marked off in tenths and hundreds. So here's what I want you all to do, for the 6 of you that are in the room. You have an index card. I want you to take whatever widget I've given you, okay? And I want you to measure the distance across here, okay? I want you to measure this. And then when you get it, then I want you to come up here and I want you to write it underneath whichever widget you have. The 0, the 1 that's marked off in tenths, and then the one that's marked off with a whole bunch of divisions. Okay? So I want you to come up here, write that down once you get it measured. I want this width across here.
You want us to write it on
Yeah,
the
right, yeah,
bars?
come up here, write it on the pad. Just write it underneath whichever one you think you have. Pencil's up there. Okay. Huh. 4 of them are right, 2 of them could be better. Okay? Not wrong, they just could be better. So, let's start with this. Who had this one? Okay, right. Okay. Would you bet large sums of money that the 0 is correct? Do you know for certain that it's somewhere between 0 and 1?
Yep.
You know for certain, okay? So how did you arrive at the 6?
A guesstimation.
Yes, right? So if you look at the pattern, we know the 0, we guessed the 6, okay? Go with this. Now, let's talk about who had the 0.64. Hey, yes ma'am. How did you guys arrive at the 6? Do you know the 6? Are you solid on the 6? Okay? How do you know? Because it's somewhere between what?
0.6 and 0.7.
0.6 and 0.7. So I'm guessing if you were to magnify that a little bit more, okay? Here was 0.6, here was 0.7, and the edge of that card was something about there, I'm guessing. Now, look at the pattern, right? You know the 0, you know the whole number, you know the tenths, you estimated the
Hundreds.
hundreds. So the pattern is that you estimate one more place than what you know for certain. Okay? Good with that? Now, if all I see is this set of measurements, if this is all I see, what do I think happened? Which measuring device do I think they had? I think they had this one. Because this looks like the exact same measurements as these do. Now, who had this Sproul? Okay, Edmund Sproul. So, if you follow this pattern, was this exactly at 0.64? So in other words, with this one, they had these tiny, 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 tiny divisions. So, if you look at what you guys had, okay, there's 0.6, 0.7. So was yours exactly on that 0.64?
It was pretty close.
Okay.
It was like maybe like very small amount off, but like
Over, this is like Vegas,
it was a
over
little
or under?
under, wasn't it?
So a little bit under, right?
Yeah.
So what you could have done is that you could have done 0.638, okay? If it had been a little bit under. So look, you know this one, you estimated this. Now, just like in many aspects of my life, zeros and freshmen give you trouble, okay? When do you use them, when do you not? So here's the situation. If it had been exactly at 0.64, that 0 is a valid guess, okay? So if it had been exactly on that, you could have written that as 0.640. Because if I see this, I know the 6, you all know the 4, you guess the 0. So zeros are like freshmen. Sometimes we need them to take up space, okay? But here's what's important. This 0 is important because of the fact that it indicates the precision of the measuring device, okay? This 0 is important. Now, here's where the door has to be able to swing both ways, okay? The door has to be able to swing both ways. So, I've got to be able to look at this and know which measuring device that you have, okay? Just like you have to be able to look at that measuring device and write down the correct number of values to indicate the precision that you have. Now, you can't go nuts and go, wow, I'm going to show Burkamp that I am a top-notch physics student. That was exactly 0.64. I'm going to put 0.64000 because I'm just that cool. Now, you can't do this either, because if you do this, then you're saying, you know, the tenths, the hundredths, the thousandths, the 10,000s, you've got divisions within divisions within divisions. And then I'm going to estimate that. So you can't go crazy with it either, okay? You can't. You can always estimate one more place than what you know. So the last digit is a guess, okay? The other ones are known. Last one, that's kind of where we have a little bit of uncertainty, okay? And there will always be some uncertainty. If we look at the mass of the Earth, okay? Mass of the Earth is 5.979 times 10 to the 24th kilograms, okay? We're not saying the mass of the Earth is, you know, 5.979324164.2 grams, okay? God, no, all right? It's pretty close, all right? So here's what you have to understand about this whole concept of significant digits and precision, okay? And if you understand one big idea, everything else kind of takes care of itself. If you have sketchy data, you can only do sketchy calculations. If you have really good data and good precision, you can do better calculations with it. But the overriding theme is that you can't make your data, okay, look better than what it is based upon your measuring device. In other words, you can't go here and randomly chuck zeros on the end of it to try and make it look better. But the other side of it is that if you have sketchy data, if you have imprecise data, your calculations can't make that look better than what you have. So in other words, if you look at these measurements, 0.6, right? This only has one significant digit, and we'll get into the rules of significant digits just right now. It's like, here's the deal with significant digits, and it all boils down to zeros and decimal places. Decimal places. If there's a decimal place, you find the first non-zero digit and you count everything to the right. So here's 0.6, this has one significant digit. Here's the decimal place, this is going to have two significant digits. You count to the right. This, let's say this actually had a zero on the end of it, which it should. Then you find the decimal place, you count everything to the right. So this would have three significant digits. So when I do calculations with this, hey, I got sketchy data. I really can't say my answer is 3.7241 whatever, because I got questionable data. I can't make my answer look better than what it is. So if you keep that concept in mind, it's like scientific integrity. You can't make your answers look better than the data that you have. Okay, if you just keep that idea in mind, everything else will take place. So let's say that we want to talk about the distance to, I don't know, the quick shop up there at 53rd and Mays. So one option is that we can go, oh, it's about a mile, that's about 900 meters, okay? So that's about 900 meters, okay? It's a decent walk. You consider a meter is like one step, so that's like 900 steps, okay? How far it is to a point, 900 meters. So if there's not a decimal place, you find the first non-zero digit and you count left. So this one is an estimate. How far is it? It's about 900 meters. I didn't measure it with a tape measure. And sometimes that's all we need. Hey, it's 900 meters. Now, if I say, hey, how far is it? And you say it's 960 meters, okay? Now that's something different. Now we're saying we know the 9. We're pretty solid on the 6. This 0 is like a freshman. It's just taking up space. Necessary, but it's just taking up space. Not significant. So, again, there's no decimal place. This is going to have two significant digits. No decimal place, you count left. Find the 6, count over. Now, you say, oh, let's say it's 964 meters. Oh, now we're getting good, okay? So now we've got a much better measuring device. Again, there's no decimal place. We count everything to the left, so this would have three significant digits. So this has